Hi, my name is Mariberto Calvillo Mendiola, and in this video I'll explain the bisection method. And for that I'll begin by giving a little overview about what this method is. The bisection method is the simplest method used to find the roots of the polynomial equations. But how does it do it? Well, it separates and subdivides the interval in which the roots of the equations lies. Given that the principle behind this method is the intermediate theorem for continuous functions, that basically consists in multiplying the lowest value in the interval that we choose, evaluating in the function that we are analyzing, times the average from both the lowest and the highest values in the interval that we also evaluate in the function, so that this value in each cycle tends to be 0. This works by narrowing the gap between the positive and the negative intervals until it closes in the correct answers. But how does it narrow the gap? Well, by taking the average of the positive and negative intervals, as we mentioned before. The bisection method is also known as interval halving method, root finding method, binary search method, or the economy method. And by looking at the whole process, it is relatively simple, but it is relatively slow as well. Now that the concept was explained, we can watch how is it that the process takes place in a graph for better understanding. In this image, we have a function that by looking at it, we have a root in the value 1 divided by p. We know that this value is between 0 and 1, but we can ask, without the graph, how do we know that we should use those values? Well, we don't necessarily need to use those values specifically. This method will work either you use either 0 and 1, or if you use, for example, I don't know, minus 25 and 53, for example. Just that with a bigger gap, we will need more cycles to tend to 0. The only two restrictions that define which range of values we can work with are that one value has to be smaller and the other one has to be bigger than the root that we're looking for, and that if it has to enclose only one root. If the values held more than one root, it will give neither of the roots. So the interval has to have only one root. How can we know which values are finite to validate these restrictions? Well, by evaluating the function in many values when the result changes between negative and positive. Now we can get to how the method is applied. For that, we consider that xi corresponds to the lower value, xu to the bigger one, and xr to the average of those two. Then the next two columns are evaluations of the function in the values xi and xr. For the method to work, we must swap either xi or xu by the average of the last cycle, and this is defined by the product of the evaluated values from xi and xr. More specifically, if it is positive, the exchange value will be xi, and if negative, the swap value should be xu. Then here we have an exercise to exemplify the process. Using this function, we use values that have the root between them, in this case 1.5 and 2.5 to exemplify. Then the average we get from those two is in the fourth column, and in the next two we have evaluations from the function using xi and xr, and in the last we have the product from those two. Having this value, we can check if it is positive or negative. In this scenario it is positive, for what we must swap the xi value in the second cycle for the xr value from the first cycle, and then make the whole process again. In the second iteration, we have that the last column is negative, so in the third, we must swap the xu value for the average from the second. This process is made the necessary times that we need to determine the root that will be the value of xr. But sometimes we need to look at the tendencies that this column has. In this case, the value gets closer each cycle at 2. Then we can define that the root in this interval is 2. But this function is quadratic, which means we have 2 roots. For what we should make another table with a different interval, that in this case I choose to use 2.5 and 4. The process is the same, evaluating and swapping, and then until we get a tendency in the xr that in this case goes between 3 and 2. Well, the upper values from 2 and the lower values of 3. And with that we can determine that the root in this, the second root that we can get, its value is 3. We have our calculations, so the last thing I'll make is check the answers in the graphic. In this graphic then we can notice that effectively our answers were right. The roots are in 2 and 3, and that's the bisection method. Thanks for your attention.